So the big idea of the paper is, why use a full kitchen? Let us use a mix of different hardware.
Have you ever used a smart assistant that can do more than just answer a question? Maybe it book a flight, summarize a document, and then add a reminder to your calendar, all from a single request. These are AI agents. They are not just single AI models. They are like digital product managers that can plan, use tools, and perform a whole sequence of action to get a job done. But these complexities create a massive challenge. How do we run them effectively without breaking the bank? I am Narottam, and today we are looking at what happens when intelligence scales but resources doesn't.
Hello, I'm Dr. Amita Kapoor, and today we are diving into a fascinating paper from researchers at Stanford and Gimlet Labs that tackles this exact problem. It is called Efficient and Scalable Agentic AI with Heterogeneous Systems. Their core idea could change how we deploy AI, making it cheaper and more accessible. And the best part, it might let us use our existing computer hardware for longer. So let us get started. First, let us understand why AI agents are so different from regular AI models. Think of a simple AI model, like the one that recognizes cats in photos, as a specialized tool, like an oven. It does one thing really well. An AI agent is more like a master chef with a complex recipe. The recipe has many steps: chop vegetables, mix ingredients, preheat the oven, bake, and then plate the dish. The chef uses different tools for each step: a knife, a mixing bowl, an oven, and a plate. The final dish is the result of this entire workflow. This is exactly how AI agents work. They are a graph of different tasks. Maybe a speech to text model, then a data lookup, then a large language model for reasoning, and finally a text to speech model to give you a spoken answer. We can visualize this as a data flow graph. Now, here is the problem the paper points out. Right now, we tend to run this entire kitchen workflow using only the most powerful, expensive, top of the line oven for every single step. We are using a $40,000 NVIDIA B200 GPU to do the job of a simple knife. It is incredibly inefficient and costly. This is because different tasks have different needs. The paper calls these workload characteristics. An LLM inference task is compute bound. It needs a powerful oven, but a tool call that just waits for a website to respond is IO bound. It is limited by the network, not the chip. So the big idea of the paper is, why use a full kitchen? Let us use a mix of different hardware, what they call a heterogeneous system. This means using CPUs, high-end GPUs, older GPUs, and accelerators from different vendors like NVIDIA, Intel, and AMD all working together. The goal is to match each task in the agent's workflow to the most cost-effective piece of hardware that can do the job well. By doing this, we can dramatically lower the cost of ownership, or TCO. But how do you actually do this? It sounds incredibly complicated. And this is where the paper's proposed system comes in. It has three clever components. First, you need a way to describe the agent's workflow that any piece of hardware can understand. They use something called MLIR, which stands for Multi-Level Intermediate Representation. Think of it as a universal programming language for AI tasks. Instead of writing code specifically for one type of GPU, you write it in MLIR. The compiler can then analyze this representation, break it down, and lower it into optimized code for any target hardware. This makes the whole system flexible and hardware agnostic. Second, you need a headship, a planner, and optimizer that decides who does what. The system frames this as a mathematical optimization problem. It takes the agent's graph, look at all the available hardware and their cost, and calculates the optimal assignment of tasks to hardware to minimize cost while meeting performance goals, like a maximum response time, which we call an SLA. Let us walk through the paper example. Imagine we have a task with two steps: pre-fill and decode. We can run them on a high-performance device that is fast but expensive, or a cost-optimized device that is lower but cheaper. If we run everything on the fast high performance device, the total time is 105 milliseconds, which meets our SLA, and the cost is 0.11 cents. If we run everything on the cheap, cost optimized device, the time is 160 milliseconds, too slow. But what if we mix and match? Prefill on high performance and decode on cost optimized? The time is exactly 120 milliseconds, meeting the SLA, but the cost drops to 0.095 cents. That is optimal choice. Finally, the third component is the orchestration system, the kitchen staff that actually executes the plan. It is a dynamic system that routes requests, manages memory and data transfers between the different devices, and makes sure everything runs smoothly in a real world distributed environment. So, does it actually work? The preliminary results are very promising. They tested various combinations of hardware on a voice agent task. The baseline for comparison was a setup of two high-end H100 GPUs, one for prefill and one for decode. The results are pretty stunning. A combination of new B200 GPU for the intense prefill task and an Intel Gaudi 3 for the decode task gave the best TCO benefit, in some cases being almost 4 times more cost effective than the baseline. But here is the most surprising part. Pause and think about this. What if you can't afford the latest and the greatest chips? The study found that using a previous generation H100 for prefill and a Gaudi 3 for decode was often comparable to or even slightly better than using two brand new B200s. This means we could potentially extend the life of already deployed hardware, saving enormous amounts of money and reducing electronic waste. It challenges the idea that you must always upgrade to the latest generation to stay competitive. So let us recap. 1. AI agents are complex workflows, not single task. 2. Running them on uniform high-end hardware is expensive and wasteful. 3. A better approach is to use heterogeneous system, a mix of different hardware. And 4. The proposed system, using MLIR and a smart optimizer, can automatically find the cheapest way to run these agents while meeting performance goals, unlocking huge cost savings and extending the life of all the hardware. The AI revolution is still just beginning, and for it to become truly widespread, we need to solve the cost and scalability problem. This paper presents a powerful system level approach that shows us a path forward, a future where AI is not just more powerful but also more efficient, accessible, and sustainable for everyone. If you found this helpful, please like, subscribe, and share it with someone who might be curious.